Thank you for the introduction. Good morning, everyone. Today, I'm going to present to you this research about piezo-resistive MEMS gyroscope for inertial navigation systems. I would like to begin with a quick overview of MEMS gyroscope state-of-the-art. Nowadays, amplitude-modulated gyroscopes still show best performances in both angle-random walk and bias stability. In the table on the right, I reported the best performance that different technologies can reach. Both and the RG are based on direct measurement of the angle. Some is based on mode match working condition, and the best one indeed is based on mode split working condition. The focus of my work is a recent innovation in the field of gyroscope. They are based on piezo-resistive gauge detection, which has demonstrated remarkably low noise and stability. Previous research with the other technologies have indeed achieved navigation great performance. However, this piezo sensor shows some advantages such as ultra small footprint, high sensitivity through IEEE dope piezo-resistive sensing elements, low capacitive peek-through, and low operating voltages. The work we present today aims to integrate high-performance electronics as initiated in a previous study. The modulation is a crucial point of the system. In fact, the zero rate offset depends on the phase error. Under mode split operation, not only the electronic delays leads to a phase error, but also there is a phase error resulting from actuating the sense mode at the drive frequency. In the graph, you can see the drive and the sense module. And working at drive frequency causes a phase error, which is higher as the frequency difference between the two modes decreases. And it also depends on the quality factor of the sense. The values goes from 0.2 degrees for a 1000 frequency split device to 1.9 degree for a 100 Hertz frequency split device at 25 kilohertz. Taking the displacement as a reference, we can see a 90-degree phase shift due to the velocity, 180 degrees phase shift due to the Burley force, and then we can find the phase error due to the MEMS and the phase error due to the electronics. In this slide, we can see a recap of what we're going to see today, starting from the MEMS gyroscope system through the description of the ASIC to the experimental results. The ASIC includes the drive loop oscillator. We read the signal through the Bristol bridge, and we amplify it through a current feedback instrumentation amplifier. There is also the automatic gain control loop and the sense chain. Instead, the automatic quadruple compensation loop is made by discrete components, and the demodulation is performed by an external lock-in amplifier. The system is powered at 10.6 volts and drains less than 7 milliampere for a total power consumption of 30 milliwatts. Since this system achieved navigation grade performances, we decided to design a new ASIC. The new release of the ASIC integrates in silicon also the automatic quadruple compensation loop and the demodulation stages, draining a total amount of current of 10 milliampere for total power consumption of 35 milliwatts, and showing an error occupation of 4.4 square millimeters. In the schematic, of the automatic quadruple compensation loop is here represented. Is an integral loop which can compensate completely the static quadrature error. The limited dynamic of the system allows to compensate static quadrature error of 860 dps, which is enough for EO gyroscopes. Then the demodulation stages are implemented by a passive mixer because we don't need a high conversion gain and we don't want to introduce 1/f noise. We use a double balance architecture in order to compensate the charge injection to the input and the output. Then a programmable delay line is placed in the demodulation references to compensate for the phase errors and perform an accurate demodulation. It's made of two sections. The first one is dimension to square the reference signal, which comes from the drive loop. And the second one is made of 32 inverters, which introduce 18 nanoseconds delay each. To let the user choose the required latency, the inverter chain outputs are multiplexed. The programmable delay line can introduce latency between 0 nanoseconds and 230 nanoseconds. Well, we can work, to introduce a negative delay, we can work not on the reference signal, but on the sense signal instead. And by placing an additional delay on the sense signal, we can center the dynamic between minus 120 and 120 nanoseconds. The programmable delay line allows to minimize the phase difference between the output signal and the reference signal taken out from the dial loop and used to demodulate the angular rate. This was dimensioned to achieve a phase resolution of 0.15 degree at 25 kilohertz and a maximum phase delay of 1.8 degree, which allows to render a frequency split up to 100 hertz. In the next slides, I'm going to present you the experimental results. We tested a 100 hertz frequency split device, which shows a sensitivity of 4 millivolts over the DPS and a linearity error of 0.2% over the full scale range of 225 DPS. Theoretically, only considering the MEMS, the phase error is about 1.7 degree. In fact, we obtain the best results with a maximum value of 230 nanoseconds. We tested also a 500 frequency split device. For this measurement, we centered the dynamic of the delay line between minus 100 and 100 nanoseconds, as previously mentioned, and we obtain a zero rate offset of 0.2 millivolts with a delay of 43 nanoseconds. In this graph, the power spectral density of the signal is reported. It shows a white noise level of 950 nanovolts over square root of hertz, which corresponds to an input referred white noise of 250 micro DPS over square root of hertz. Unfortunately, we had a high flicker noise at the output. Currently, we're still investigating the causes of this flicker noise. We suppose that it goes by a buffer, which is not in the core, but it's in external circuit. And it's not well dimensioned to limit the flicker noise in the baseband. In conclusion, the work presented today represents a significant advancement in the development of miniaturized sensors. The programmable delay line mechanism has allowed to minimize zero rate offsets, and in terms of angle random walk, we are already achieved navigation grade performances, and mitigating the extra flicker noise at the output. We should achieve also good stability performance. Our research paves the way for integration of high-performance electronics with piezoresistive base sensor, opening up new possibility for compact and efficient navigation system in various applications. If you're interested in this research, you can already find the manuscript on Sensor Letters, and thank you for your attention.